Okay, the other day we did exponential functions in class. You had to write equations, and they all looked like something times a number with an exponent. Most of you were putting it into a parentheses. Either way is fine, because either way, always remember that you have to do the exponent first, then multiply by whatever number a is. Okay, so we're going to graph these, and it helps to have a calculator, but some of the ones we're going to do you can actually do without a calculator if you feel like it. So let's start with the first example. So we did a lot with percents. We did 1 plus 8%, so we had 1.08 to the x. Well, these you're just going to see some simple numbers, which for the sake of graphing, it just makes it a little easier. I'm sure you don't mind. So we're going to plug in each of these x's for the exponent. So I'm going to do a couple kind of slowly. Obviously, you can use a calculator, like I said, but basically you're just plugging in each of these for the exponent. I know 3 to the negative 2 is 1 over 9 times 2 is 2/9. I just like that better than the decimal on the calculator, but it doesn't matter. It's a very small number. Just remember that when we're graphing it. If I put in negative 1 in for the x, well then it becomes 2 times 1 over 3, because 3 to the negative 1 is 1/3, so it's just 2/3. So again, it's a small number, but a little bit more than half. And you'll see that in the likeness of a decimal as something over 0.5, which in that case it's 0.6 repeating. So that's fine if you're putting decimals in. I'll leave that up to you. Now we're getting to where we should have some easier numbers to work with. So 3 to the 0 we know equals 1. 2 times 1 is 2. 3 to the first is 3. 2 times 3 is 6. And 3 to the second is 9. So 2 times 9 is 18. And that's why you kind of have a funny looking graph over there. Hopefully it looks better on your paper than on my screen. We're just going to graph these points. So starting at negative 2, I'm going to go up just a tiny bit. Go ahead and graph along with me or on your own, however you want to do it. So negative 1 and up 2/3. 0 and up 2. 1 and up 6, I think is right here. And you can really see the increasing now. So when I go over to 2, it goes all the way up to 18, which is the last point that's going to fit on my graph. And if we kept going in the negative direction, if I kept putting in negative exponents, we're going to keep getting smaller and smaller numbers, but they're always going to be positive numbers. So when I go to actually fill these points in, I'm going to connect these and they kind of curve down. And this actually just keeps getting smaller, 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 which is really hard to draw. But keep that in mind, that it never really gets down to 0. It just makes a really, really, really small number, but they're always positive. That's actually, that has a name to it. It's called this asymptote. Not super important right now, but that's what that means. It's a line that the graph approaches but never actually intersects with it. So in this case, the x-axis would be known as the asymptote. Alright, so we have another graph on this page, and what I'd like you to do is maybe try it by yourself first. So plug some numbers in, and then you can come back and kind of check with me. So pause the video here if you need to. Okay, hopefully you've got your table filled in. Those are the numbers that I got. As you can see, this one gets smaller. So let's start graphing it. So negative 212, negative 1603, 1.5, 2 3/4, and you can see it's the same thing as the one above it, except It's decreasing. So it does get smaller, smaller really fast. Then it starts to slow down, but it's still getting smaller. Same thing we talked about up above. It's never going to actually go to 0, and it's never going to be a negative. So it's just going to approach that x-axis, but never actually touch it, which is hard to draw, I realize, but just do the best you can. So the first one, I'm going to go backwards here. The top one, it was increasing. And think about when we were writing equations for the word problems, this number right here, when something increased, you did 1 plus the percent that it increased every year or every week, or whatever the situation was. So anything that's greater than 1, so if, I'm going to go back up here, sorry. If b is greater than 1, it's going to be an increase on the graph as I go left to right, like I'm reading a book, right? And then the second one that we graphed, that number b is less than 1. And these were like the decay problems or the depreciate problems, the things that said they depreciated or went down in value. We had 1 minus the percent that it decreased, and so it made that number less than 1. So if we have a number for b that is less than 1, it's going to decrease. Okay? One more thing. I want you to notice on the first example, the y-intercept. So look at it and pick out the y-intercept for me. I see a y-intercept of 2. And on the second graph, pick out the y-intercept again. I should have gotten a y-intercept of 3. So looking at the table, that's where x equals 0. And looking at this other table, it's where x equals 0. That always ends up being your y-intercept. Looking at the equations, it makes sense. If I plug in a 0 for the exponent, it's basically going to cancel out that number because everything to the 0 equals 1. And then you take that 1 times a. So that's another note that we can make up here. A always equals the y-intercept. No matter what b is, if I put a 0 in for x, I'm going to turn this into a big number 1. And then a times that number 1. Sorry, is going to be my y-intercept. All right, save these notes.